So what exactly is gauge pressure? So the gauge pressure is going to refer to the pressure of some system without regarding the atmospheric pressure. So it's going to be the pressure of this system minus the atmospheric pressure, because normally on Earth, when we're talking about pressure, we have the pressure of our system, but we also live in an environment where we have this atmosphere of pressure constantly exerting a force on us, which is 1 atmosphere of pressure. That's the unit for it, or about 10 to the 5th pascals of pressure that this atmosphere is exerting on us. So when we measure the gauge pressure, we're going to subtract this pressure to get our gauge pressure. And so let's go ahead and look at an example of this. So let's say that we have some container of water. So some container of water here. And then we're looking at a surface. So let's say a flat surface. This is our object that is floating here in the middle of the water, right? So we want to get the gauge pressure of this. So what are all the pressures that are being exerted on this object right here? Well, we have the atmospheric pressure, which is the air column above this. But remember, we're calculating the gauge pressure, so we're not regarding that atmospheric pressure. So the only other pressure in our system is going to be this fluid, right? The weight of this fluid is giving a pressure, exerting a pressure on this object because it is submerged under this. So to get gauge pressure, or since this fluid is at rest, another way to say this is the pressure of a fluid at rest. So P for pressure of our fluid at rest. So the gauge pressure of our system. So to get this, we use the formula rho, which is density, times g, acceleration due to gravity, and h, so the depth or the height beneath the surface of the fluid. So the surface right here, surface of water. Our object is down here. So this height or depth is going to be our h. That's what we would use. So rho, density of our fluid. So whatever the density is of the fluid, that's what you would use to calculate that. Acceleration due to gravity, same number. It's a constant, 9.81. And our height or depth below the surface of the fluid. And so when we're looking at this, we can see how density normally would be a constant if it's just one fluid. So that would be a constant. G is going to be a constant. Acceleration 9.81 is always going to stay the same. And so really the only difference here that we get is with the depth. So this tells us that the deeper that our object is, so let's say our object is right here, the deeper the object is, then the fluid's gonna exert more pressure due to the weight of the water above it. So this object being here would have less pressure exerted on it versus this object right here, because it's at a lower height or a lower depth or more depth under the surface of the water. And so here's just like another example that you can kind of view this. So if our object was then at the surface of our fluid, then our height would be 0 because that's where we're measuring from. And so this whole pressure of a fluid at rest exerted on our object would be 0. That would be our gauge pressure. So the only pressure acting on this object would be the atmospheric pressure here. So P naught. That would be our atmospheric pressure, but because we're measuring the gauge pressure, that would just be 0, because that's the only pressure, the atmospheric pressure. It's once we get to a certain depth below that fluid, then we get the pressure of the fluid plus the pressure of the atmosphere. But if it is just floating on the surface, let's say, there would just be atmospheric pressure and none from the fluid itself until it gets a certain depth or any depth below the surface of our fluid. And so that's gauge pressure.